I recently wrote a series of posts talking about the stability of some frames. There were 3 posts. I'm showing them here. There was some good engagement. People gave their opinions, shared their thoughts, so I really appreciate that. And I'd like to go through the thought process that I would employ to determine if these were stable or not. So let's start with the first one here on the left. It's this structure here. As you can see, I'm counting the number of supports and restraints and connections that the structure has, and it clearly has enough because we have 2 solids. That means we need 6 constraints, and there are 6 constraints. So we have the right number of them. The question is whether the structure is stable in the sense that are the constraints placed correctly to prevent the structure from moving, at least in a first order analysis. So if we look at this structure here, we have 2 solids. I've colored them in blue and green. The first one can rotate about this point here on the left support, which means that if it can rotate about that point, and we draw the line connecting that support and the hinge, that hinge has to move this way, right? Perpendicular to that line. But that represents one constraint for the location of a possible instantaneous center of rotation of the second solid, the one in green. But we have other constraints for where that center of rotation needs to be. Well, it also needs to be along this line. Why? Because this support can move sideways, and so if it does, wherever that center of rotation is, it would have to be along that line so that it can move, that support can move perpendicular to that line. But it also needs to be along this line so that this support could move sideways like that. Well, we have basically 3 constraints on that solid for where its center of rotation should be, and those constraints are incompatible because these 2 lines meet at this point, but then the third line does not go through that point. Therefore, it's not possible to find a mechanism, and that confirms that the structure is stable. The second case was this one, which is somewhat resemblant of the first case, but there is a big difference, right? The big difference is that now instead of having 2 members that are rigid, we have 3, because the 2 members on the right are not rigidly connected to each other, like in this case. They are both meeting at the hinge. Now, if we simply do the count, we immediately realize that this is unstable because we have 2 constraints here, 1 here, 1 here, right? And then we have 2 connecting here, and then we have 2 connecting here. So that gives us 6 and 2, that's 8, and we need 9. So it's clearly unstable. It does not have enough constraints. But it's still useful to go through the exercise of thinking where the center of rotation of these members would be, which we should be able to find a mechanism because we don't have enough constraints. For the member on the left, it will rotate about this point, which means that this line here represents a constraint for both of the members on the right, because that point needs to move jointly with everybody. Now, if we look at the member here in yellow, which is this one here, we had this one in blue, so let's highlight that. this member has a constraint along this line. So you can see that it meets at this point. It doesn't have any other constraints. So that member will rotate about that point, and it is compatible with the fact that that support moves sideways and that that joint moves perpendicular to that line. Similarly, for the member in green, it presents this vertical constraint here due to the support. Center of rotation is there, rotates about that point, compatible with this moving sideways and the joint moving perpendicular to the line. So basically that's the mechanism in which that structure would tend to move. Right? This being the center of rotation of yellow, this being the center of rotation of blue, and this being the center of rotation for green. And finally, let's look at this one, which is a very interesting case. We have here 4 members connected in this way. And if we look at all the restraints, we realize, first of all, that we just don't have enough supports, right? Because you could think of this as 2 members connected with 2 horizontal links, and so in that case you have 2, 2, and 2, and 1, sorry, on the right, and that's 5. We need 6, so it's clearly unstable. The question is, where would the center of rotations be? And we can go through a similar analysis to what we did before. And so the member blue here on the left would have a center of rotation at the hinge. These 2 joints here on the left of the connector have to move in this way as shown. And in order for member 3 to rotate, then its center of rotation has to be here as shown in purple. That makes the displacement compatible with the center of rotation of element 1. Similarly, for element 3, the center of rotation is as shown. And now the interesting thing is, where is the center of rotation of the green solid, number 4? Well, it turns out that the center of rotation of that solid is vertically up at infinity. And if that's the case, then you can see all the points connecting solid 4 with 2 and 3 move in a perfectly compatible fashion. So here you can see the arrows indicating the movement of all the points that are able to move, and definitely the structure is unstable, and this would be the mechanism. But now someone suggested this variant on the problem. Now what if we added 1 constraint to the right support here, right? And instead of making that a roller, we make it a hinge. Now is that stable? These are still rigidly connected. Now initially, even I thought like, oh yeah, that's stable, but it's not stable. It's not stable because if you look at the instantaneous centers of rotation and the compatibility of the motion, basically this is how we would move, right? So this is the right side, and this is the instantaneous center of rotation. Now these joints here shown on the links have to move according to that line perpendicular to it, right? And then on the right, for similarly, right? If this rotates like this, then these points on the right side of the links have to move as shown, and you can determine that the center of rotation of, let's say, purple would be up here, and the center of rotation of yellow would be here. And all of those displacements are compatible, which means that the structure is also unstable. That's a really nice problem. And so there you have it. Some of these problems can be a little bit tricky, but with patience and thinking about compatibility of displacements and rotations, you can determine whether these structures are stable or not, in addition to them having the right number of restraints. Like in this case, right? We have the correct number of restraints, 6, but the structure is actually unstable. So we have all cases here, right? The correct number of restraints, unstable. The incorrect number of restraints, and unstable, as in these two cases shown here. And then the correct number of restraints, but actually unstable. Thank you.